Lab 4 by Madeline Gaffney. Lab 4 instructed me to predict the motion of a spring mass system as a mass oscillates and swings in an arc. The approach that I took used physics concepts such as Newton's second law, Hooke's law, the energy principle, and I used methods such as analysis and tracker and a module created in VPython to predict the motion. The result is that the computational model created predicts the experimental motion well, but does not match up completely with the observed motion due to human errors. The physics behind this lab include Newton's second law to update the object's position, their energy principle to calculate the energies of the system, such as kinetic, potential, and spring, and Hooke's law to make calculations regarding the spring. Here's what it looks like when I analyze the video in Tracker. I set up an XY axis with the origin at the top of the spring. I use the length of the spring as the length of the calibration stick. I then use the tracking tool to track the object's motion as it oscillates. The resulting data is found in the table in the bottom right corner. Using given information and data found through an analysis and tracker, I found these initial conditions. The initial mass was 0.402 kilograms. The initial position was negative 0.11, 0.688, 0 meters. The initial velocity was 0 meters per second. The initial time was 0 seconds. I calculated the spring constant to be 6.87, and I calculated the relaxed length of the spring to be 0.127 meters. The final time of observation was 9.212 seconds. Here are my calculations for the relaxed spring length and the spring constant, which are both needed to initialize the code. Using the initial conditions and physics concepts discussed, I made the necessary modifications to the code to create my model. The top half of the code is for the visual part of the model. In the bottom half, I updated the ball's mass, position, velocity, and initial time to reflect the initial conditions. In this part of the code, I inserted the spring constant and the relaxed spring length that I calculated. I then updated the equation to calculate the spring force. I updated the equations in the bottom half of the code to reflect the energy principle and calculate the system energies. In this piece of code, I updated the equations to calculate the gravitational force, spring force, and net force. I also included equations using Newton's second law to update the object's velocity and position. I then modified the equations to update the spring force and then included equations from the energy principle to calculate energy changes of the system. I then used these changes in energy to contribute to the graphing part of the model. Here's what happens when I run my model. In order for the energy principle to be satisfied, the delta E of the system must be equal to 0. Since the yellow line when I run my code is equal to 0, the energy principle is satisfied in my model. For the second part of what does it mean, I calculated the x component and y component of the motion separately. For the x component, it moves in an arc-like motion like a pendulum from left to right. The y component of the motion is spring-like and moves up and down. The equations to calculate the period of the x component and the y component of the motion are different, and the period for the x component is greater. Since the equations to calculate the period for the x component and y component of the motion are completely different, the resulting periods should be very different, as mine are. In conclusion, the computational model created in VPython with the use of the data found in the tracker analysis creates a pretty accurate prediction of the motion of the mass, but it does not match completely due to possible human errors, such as mistakes made while tracking the object's motion in tracker.